Section: Introduction. In this section, we outline how we create a model-specific dataset, focusing on generating examples of hallucinations that occur despite having the correct knowledge, which we refer to as HK+. We start by classifying examples based on the model's knowledge. Any instance where the model lacks knowledge is labeled as HK. For examples where the model knows the correct answer, we then create scenarios where hallucinations can still happen, leading to HK+ cases. We concentrate on closed-book question answering tasks that require short answers. In our setup, the model receives a question and generates an answer, which may either match the correct answer or be a hallucination. We view knowledge in the model as existing on a spectrum. At the low knowledge end, there is little to no connection between the question and the correct answer, making hallucinations more likely. Conversely, at the high knowledge end, there is a strong connection, but hallucinations can still occur. To analyze this, we focus on the extremes of the knowledge spectrum, high and low. For our model, we generate multiple responses to a question and check if the correct answer appears. We perform one greedy generation and 5 additional generations with a moderate temperature setting. If the model fails to produce the correct answer in any attempt, we label it as HK. If it generates the correct answer in all attempts, we then classify it as either factually correct or HK+. Section Summary. In this section, we outline our methodology for creating a model-specific dataset that distinguishes between two types of hallucinations in large language models: HK, where the model lacks knowledge, and HK+, where the model has knowledge but generates incorrect responses. We focus on closed-book question answering tasks, categorizing examples based on the model's knowledge and generating scenarios that induce HK+ hallucinations despite the model's correct knowledge. Section: Hallucination despite knowledge. In this section, we explore the concept of hallucination despite having knowledge. To classify a high-knowledge example as either factually correct or as having hallucinations, we refer to previous work that showed how a model, after giving an incorrect answer, often generates a flawed explanation to justify its mistake, a phenomenon we call the snowballing effect. We also note that similar behaviors occur when we use persuasion techniques or weak semantics in prompts. We believe these scenarios are crucial to examine because they highlight errors in the prompt, which can stem from either the user or the model's earlier outputs. Regarding user mistakes, we recognize that users may not always have perfect knowledge. They can provide incorrect facts or make grammatical errors. If these mistakes lead the model to hallucinate, it presents a real-world issue that we need to tackle. On the other hand, the model can also create a snowballing effect by making errors in previous responses that get included in the prompt. If the model hallucinates, we want to prevent this from affecting future outputs, so we must address this problem as well. To help generate high-knowledge hallucinations in large quantities, we design two synthetic setups: A. Bad shots, which utilize the snowballing effect, and B. Alice-Bob, which employs persuasion and weak semantics. We later show that one setup can generalize to the other, validating our approach to studying the phenomenon of hallucinations despite knowledge. In the bad shots setting, we demonstrate how errors in context can lead to a cascading effect that undermines the accuracy of the model's future responses. To replicate the snowballing effect on a larger scale, we introduce a method called bad shot prompting. We create 20 false question and answer pairs using ChatGPT 3.5, where the incorrect answer is semantically similar to the correct one. For example, if the correct question is, which element has the chemical symbol H? With the answer, hydrogen, a bad shot version might be the same question with the answer, helium. For each target question in our evaluation set, we prepend 3 random bad shot examples, simulating potential mistakes from users or the model itself. This approach allows us to gather numerous instances where models hallucinate even when they possess the knowledge to respond correctly. In the Alice-Bob setting, we focus on persuasion and weak semantics instead of using bad shots. We start the prompt with a scenario where Alice and Bob, 2 students, are preparing for a test, and we include a one-shot example at the end. This setup is subtler than the bad shots approach and results in fewer hallucinations. By incorporating deliberate mistakes in the prompt, we aim to create a persuasive context that suggests Bob is not very smart and that the test is challenging, while also implying that only a minimal score is needed to pass. For our dataset construction, we utilize our method for distinguishing between low and high knowledge examples and label high knowledge instances. We draw from two well-known closed-book question answering datasets, Trivia QA and Natural Questions. We test three models: Mistral 7B v0.3, LLAMA 3.1-8b, and Gemma 2-9b. We find that even in the bad shots setting, most high-knowledge examples are labeled as factually correct rather than hallucinations. However, we still have enough cases of hallucinations despite knowledge to analyze further. In the Alice-Bob setting, we observe similar patterns, though with fewer hallucinations. For more details on dataset construction, we refer to the appendix. Section Summary. In this section, we explore how user and model errors can lead to hallucinations in AI-generated responses, introducing two synthetic setups: bad shot prompting, which simulates cascading mistakes, and the Alice-Bob setting, which employs persuasion techniques. Our findings indicate that despite the presence of knowledge, models can still generate incorrect answers, highlighting the need to address these hallucinations in real-world applications. Section: Implementation Details. In this section, we aim to highlight the significance of distinguishing between two types of hallucinations and utilizing our model's specific dataset to enhance detection methods. We will present various experiments focused on identifying different hallucination types by training classifiers on the model's internal states. For our detection experiments, we randomly select 1,000 examples from each label in each dataset and divide them into 70% for training and 30% for testing. We employ a linear classifier for detection, consistent with previous studies. The detection results discussed in the main paper are based on hidden states from the residual component after each transformer block, with additional results for the MLP and attention components available in the appendix. Each experiment is repeated using 3 random seeds for the SVM, and we report average results along with standard deviations. To ensure consistency with the prompts used in creating the hallucination despite knowledge dataset, all examples utilize similar prompts, specifically bad shots or Alice-Bob. Unless stated otherwise, results are presented under the bad shot setting, and we include examples that consist of the concatenated model-generated answer, which may or may not be a hallucination, along with the prompt and question. All experiments are conducted on an NVIDIA RTX 6000 Ada with 49 GB of memory and 4 CPUs, taking about 2 weeks to generate all datasets and results on a single GPU. Next, we investigate whether different types of hallucinations are represented differently within models. We first explore the distinction between hallucinations that arise from a model's lack of knowledge and those that occur even when the model has relevant information. This differentiation is essential for understanding the mechanisms behind hallucinations and developing effective detection and mitigation strategies. We analyze the model's inner state to show that it represents these hallucinations differently. This task is challenging because it requires us to distinguish hallucinations from factually correct responses and identify the type of hallucination, which involves understanding the model's knowledge. We categorize the scenarios as follows. 1. The model knows the information and does not hallucinate, factually correct. 2. The model knows the information but hallucinates, HK+, and 3. The model does not know the information and hallucinates, HK. Our findings indicate that detection accuracy for these 3 classes across the model's layers is between 60% and 70% at the highest layer, significantly above the random baseline of 33%. Additionally, when we assess the accuracy of any 2 of the 3 classes in the middle layer, we find it to be no less than 70%, suggesting that the model's inner states contain valuable information for differentiating between these cases. Similar trends are observed in the Alice-Bob setting, although the results are lower due to the subtlety of this setting. We then examine whether the bad shot and Alice Bob synthetic settings are effective for studying hallucinations despite knowledge, HK+. We assess how well a probe trained on the bad shot setting generalizes to examples from the Alice Bob setting. This presents a challenge due to the differences in prompts between the two settings. In this experiment, we focus on differentiating between HK+ and factually correct examples. Our results show that while changing the training setting reduces performance by up to 10%, it still exceeds the random baseline, indicating some level of generalization between different settings for inducing hallucinations despite knowledge. This supports the use of synthetic datasets for studying this phenomenon. Finally, we compare WAC datasets created for different models and evaluate hallucination detection using model-specific versus generic datasets. We demonstrate the variability in knowledge and hallucinations across models by measuring the Jaccard similarity of WAC datasets generated for different models. We calculate the Jaccard similarity for high knowledge examples in two models and for HK+ examples in shared knowledge cases. Our findings reveal that knowledge similarity for natural questions is around 0.6, indicating significant divergence, while for trivia QA, it is about 0.8. We also find that hallucinations in shared knowledge cases are mostly similar, with scores between 0.8 and 0.95, but a difference of 0.1 to 0.2 suggests unique hallucination patterns for each model. The bad shot setting shows lower hallucination similarity than the Alice Bob setting, highlighting greater diversity in hallucination patterns. These results emphasize the need for model-specific approaches to hallucination detection and mitigation, as both knowledge bases and hallucination patterns differ across models and datasets. Section Summary. In this section, we demonstrate the significance of distinguishing between different types of hallucinations and utilizing model-specific datasets to enhance detection accuracy. Our experiments reveal that models can effectively differentiate between hallucinations arising from knowledge gaps and those occurring despite having relevant information, highlighting the need for tailored detection strategies based on the unique characteristics of each model. Section. Detecting a model's hallucinations works better with a model-specific dataset. In this section, we demonstrate the significance of using a model-specific dataset rather than a generic one for detecting a model's hallucinations. We begin by outlining how to create a generic dataset before moving on to our experiments. A generic dataset is a labeled collection that does not consider the specific hallucinations or knowledge of a model. This approach is commonly used in hallucination research for both detection and mitigation. For our comparison, we also develop a generic dataset. Typically, we construct a labeled question-answer dataset using a triplet: a question, a correct answer, and a hallucinated answer. We create a hallucination by adding the incorrect answer to the question, while a correct example includes the accurate answer. This labeling is based on the correctness of the answers according to general knowledge. However, many datasets only provide the correct answer, which means we need to generate the hallucinated answer. We do this by prompting a language model to create a plausible but incorrect response. The resulting dataset is similar to our model-specific datasets but differs in the source of hallucinations. The hallucinations in the generic dataset are not tied to any specific model and mix up causes like lack of knowledge and hallucinations despite knowledge. In contrast, our model-specific datasets focus on hallucinations that are unique to each model. Our results indicate that the generic dataset is ineffective at identifying hallucinations that occur despite knowledge. We compare two settings: one that is model-specific, distinguishing between hallucinations despite knowledge and factually correct examples, and another that is generic, separating hallucinations from correct examples. We test these on a model-specific set of examples. To make the datasets comparable, we include problematic examples at the beginning of the prompt in both cases. Our findings show that classifiers trained on generic datasets perform poorly compared to those trained on model-specific datasets. The model-specific classifiers maintain high accuracy, highlighting the benefits of customizing hallucination detection methods for individual models. This aligns with previous research indicating that generic detectors perform worse on specific datasets than those trained directly on them. We also explore the potential for preemptive hallucination detection using model-specific datasets. Our earlier detection results were based on hidden states after the model had processed the answer, which may have already included a hallucination. A key advantage of model-specific datasets is their ability to detect potential hallucinations before they occur, which is not feasible with generic datasets. We analyze this capability using our WAC dataset, where each example consists only of the question without an answer. This allows us to assess the model's tendency to hallucinate based solely on the input query. In contrast, generic datasets typically rely on the answer for labeling, providing no indication of potential hallucinations before generating a response. Our results show that model-specific preemptive detection yields promising outcomes, while generic post-hallucination detection performs poorly, often at random levels. Additionally, model-specific detection after generation shows varied results, with some models achieving detection rates of 60% to 70% on one dataset, while remaining low on another. We conclude that post-hallucination detection is not effective for preemptive identification, further emphasizing the advantages of model-specific datasets. Our research focuses on different types of hallucinations and develops a method for constructing hallucinations that occur despite knowledge. It is related to existing studies on hallucinations and the concept of jailbreaking. Section Summary. In this section, we demonstrate that using a model-specific dataset significantly improves the detection of model-specific hallucinations, HK+, compared to a generic dataset, which fails to effectively identify these nuances. Our findings indicate that model-specific datasets not only enhance detection accuracy but also allow for preemptive identification of potential hallucinations before they occur, a capability that generic datasets lack. Section: Hallucination Detection. In this section, we discuss hallucination detection. We can detect hallucinations by treating the model as a black box, asking questions, or sampling its outputs. Another approach involves examining the model's hidden representations by training a detection classifier. While much of the previous work used general datasets, we focus on model-specific datasets. Some earlier studies did look at model-specific hallucination datasets and highlighted their significance, but they did not distinguish between the different causes of hallucinations. We also address jailbreaking, which involves techniques that lead large language models, LLMs, to produce unexpected or incorrect answers. For example, there is a phenomenon where once the model outputs a certain response, it is more likely to give an incorrect explanation for that response. Research has shown that a model's answers can be influenced by factors like persuasion, lengthy conversations, fantasy scenarios, LLM personas, and prompts that are outside its training data. These findings indicate that the accuracy of a model's output is affected by various aspects of the prompt, allowing for hallucinations even when the model knows the right answer. While previous work has focused on identifying methods that induce hallucinations, which can result in positive hallucinations, we directly investigate the positive hallucination phenomenon and its connection to negative hallucinations. Additionally, we present a method to automatically create the WAC dataset for further analysis.